It is with great emotion that I'm starting this. I'm very honored to be invited at this prestigious conference. ACCU is the best in England, right? Agreed? Right. Let's keep it that way. 1 hour from now, I don't want it to be a formally prestigious conference. Okay? All right, so Julie also asked me to make a couple of other announcements. Please turn off your cell phones. Lunch will be served as usual, at the usual time. And what's here? Oh, no go-to users are allowed in this room. Julie, what? So look to your left and right, and if there's anyone, security is at the door to escort them out. So, today, there's treasure everywhere. You just gotta look for it. This is a talk about efficiency. However, it's also a keynote, and I don't know how to deliver a keynote. So my working title was how to write and deliver a keynote. So I asked a few friends who are more versed in delivering keynotes and asked, what's in a keynote? What should I do? And they said, oh, this is great. Just talk about anything you like. Like Andy Warhol, like paint what you like. And he painted, I like soup. He painted soup. And that was it. He became famous. So, and the other said, should have no code and no math. It should be some sort of a fluffy thing, just feel good kind of thing, a keynote. This is exactly the kind of talk I wouldn't go to. So this talk is going to have code and actually implied math, algorithms, right? And measurements, because it's a talk about efficiency. But this thing about talking about things I like is kind of intriguing. Because consider this, what if I talk about something I like and you don't like? So that's asked my friend, and he said, oh, you don't care, you don't want to keynote the same conference twice. I mean, imagine I put that on my LinkedIn resume, and there's this guy reading and, delivered keynote ACCU twice. Jesus, Janet, I found our next CTO. It's not going to go like that, right? All right. So things I like. So it's really interesting to think about things you like. And of course, I can't put here talking about things I like because we would enter infinite recursion here. So one thing I like is confusing aphorisms. Let me give an example. You know about this, right? When you hear hoofbeats, think horses, not zebras. The meaning being, go with the most probable, right? So use probabilities and likelihoods and all of those nice things from statistics that we know from college. And I was thinking, must confuse the hell out of Africans. What do you mean? We don't have horses. What, all of that statistics stuff they teach in college doesn't apply? Jesus, what's wrong with these folks, right? So it must be very confusing to Africans. Going forward, I like fast code. We're going to talk about it today. And there's one more thing I like. I like C++ concepts. And in order to explain why I like C++ concepts, we need to take a fork in the road. I have two sets of slides. I have the politically correct slides, and I have the other slides. Hands up if you're on the politically correct slides. Nobody. All right. 0. All right, so we're in together going forward, okay? In order to explain what I like about C++ concepts, I need first to talk a bit about toilets. It's not what you think. It's not what you think. So give me a minute here. Let me explain. I can explain. Famous last words, right? So there's a company called Toto that makes a wonderful washlet. Anybody who's been to Japan? Who's been to Japan? Awesome. I'm sure you can confirm, when you come back from Japan, you feel like you're going back in time, in the Middle Ages, because they have washlets. They have these wonderful toilets that wash. It's awesome. It's like going to the future and then you return. It's like, oh my God, what am I doing here? This is so dirty, right? They have these awesome, yes, Peter.
You can get those in Switzerland as well.
You can get those in Switzerland as well. And you can get those in the States as well. So, it looks like it's like a toilet cover, and it has a little panel on the right with buttons, and, press buttons and it washes and whatnot. Awesome. So, this company offers in the States 8 washlet models, of which 1 does not have a remote control. That's the one I bought. I bought the entry-level model. I'm not kidding. All right, so picture this. Remote control on a toilet. You got to make sure that your partner, yeah. So this is kind of interesting. Like, I was thinking, what's the motivation behind that? Because sitting on the toilet is the very definition of a captive audience. You can't be in the living room and say, I could use a wash right now. Honey, where's the remote? It's just boggles your mind, doesn't it? But I figured that washers with remotes are a thing. And here's why I think are a thing. Because they combine 2 nice things. What's better for a guy? Sitting on the toilet and flipping channels. It's perfect. It's like genius. So they sell, right? 7 models out of 8 have a remote control. I'm not kidding. The remote control on a toilet. They're complex and interesting. It's like technology. It's electronics. It's not an electrical device. It's an electronic device, right? Modern and cool, but unlikely to be very useful in practice. And kind of oddly, this very list is what I think about C++ concepts. That's why I needed to take this little departure, right? There's a great blog post. Why concepts didn't make C++ 17. So it's a fascinating read. It's amazing. You gotta go and read it. It's a blog, just Google for it. Amazing. And there are like several reasons listed, and one of them was there was not enough time. When did it start? After like 4 versions. Starting 2003. 13 years. There was not enough time. And there's like one guy working on them on his spare time. And all the community was like, 2 million people was kind of waiting for that one guy to be done. Not enough time. Another interesting thing is the concepts TS does not specify any concept definition. So much about test-driven development, huh? But wait, there's more. This is like the most amazing thing. Use of concepts sometimes results in worse error messages. The first paragraph in the first proposal for concepts listed better messages as the prime motivator of concepts. First paragraph of the first proposal. It's there at the top. It's the first thing. They say, we're going to have better error messages. And then, they, just so happens, they go through with it, and in the end, like, what? Sometimes we get like worse error messages. Picture this. We have an encryption routine. Sometimes, only sometimes, it produces clear text. not clearer than it was. It makes for better literature. You put like a bad writer, you get Shakespeare back. Sometimes, not all. Most of the time, you get good encryption. Or we have a sort routine. Sometimes it increases entropy of the data. It scrambles even more the data that was there. So I find it kind of interesting. So what I'm going to be looking forward to is the next blog post, which is going to be why concepts did make C++ 20. Just bear with me for a second here. Bear with me. So maybe, humor me. Maybe. Just work with me a little here. Maybe. If 13 years was not enough, and if sometimes the error messages are worse, just maybe it wasn't such a good idea. Just a hypothesis I'm putting on the table here. Right? Enough about that. Let's talk about sentinels. Who knows what sentinels are in programming? You put a sentinel, you optimize a bit, yeah, you save a bit of tests. Remember linear find. I sprang some decode on you. This may be the first year ever I can spring some decode on somebody unannounced and not be left out the door. So I'm going to use D for a couple of reasons. But don't worry, if you don't know D, there's no problem. This find function is generic. It takes any range and any element type. Range and E, these are template parameters, as it were. And these are the normal function arguments. So this is the syntax for introducing a template function. And the range must have 3 primitives. It must be testable for emptiness. It must be able to advance, pop front. And it must have access to the first element, front. So I'm moving through the range left to right. And as soon as I find the search element, I'm going to break the loop. And then I'm going to return the balance of the range. What's left? So I'm going to position the range at the found element. If there's no element found there, what am I going to return? The empty range. So I'm going to exhaust the range. And this is a very useful function. It's akin to find in STL with iterators. It may return the end iterator. In this case, it returns the empty range. No surprise here. Implemented many times in many languages, many APIs, many, et cetera, et cetera. So how do we apply a sentinel to this? Sentinel. Before we do that, let's discuss indexing. So a range may be indexed, or we could use just this sort of like linear approach. Which one do you think is faster? Like indexing versus just bumping the pointer. Who thinks like just pointers are going to be better? Pointers? Indexing? The rest abstain? Same. The same. Okay. It depends. Right. So so this kind of changes every couple of years. It's kind of weird. So by my measurements, it's just a slight edge for indexed access. I just measured. So my explanation is that there's less aliasing, so the compiler has a better time optimizing code. If there's one pointer and a bunch of indexes, it's easier for the compiler to figure things out than with multiple pointers. And one nice thing is that the CPU has very sophisticated means to do index addressing. So it has like a unit that in hardware does all the addressing arithmetic. So, why not use indexing? So let's do that. So I'm starting with an index, and I go from 0 to the length of the range. And I'm going to bump the integer, and if the range at this position is the element, then I'm going to break the loop. And here I'm going to return the balance of the range from the ith element all the way to the end of the range. Right? Again, even if you don't know D, it's quite clear what's going on here, right? All right, let's make this faster. Finally, we got to the part where we want to optimize. So how do we make this faster? Talk to me. Talk to me. Put the sentinel at the very end, right? And do search, and we get rid of this test, right? And if the comparison is cheap enough, then we're going to be able to measure something, right? Nice. So let's do that. I'm going to save this guy into a temporary. I'm going to plop the element into the last element of the range. And here I'm going to enter a scope, because what I want is to automatically, whatever happens in this loop, I want to make sure that I'm restoring the range to where it was, to its former glory, right? This is important. Yeah, I don't want searching the range to modify the range, right? So I want to make sure in any case, even though, for example, comparison throws an error, or I have like some weird stuff going on, I want to restore the range to where it was. And here I'm going to do a little fix-up, right? Because, you know, I found the last element, and I've got to make sure that if it's the last element, I got to look a bit better, you know. Was I looking at the right thing or not? And if not, I'm going to bump I and so on. Make sense? OK, so there's a number of unexplained things here. By the way, I just got news yesterday. So this is like scope exit executes any statement automatically when this scope is going to be exited. And I found out yesterday that Peter Summerlad has a proposal for adding a similar thing to C++.
Requiring a lambda.
Requiring a lambda. All right? Thunderous applause. OK, thank you very much. Those were for Peter. All right. Awesome. So, is this going to be measurable, faster? What do you think? Slower. Who's with the same? Who's with faster? This is going to be faster. Depends on the size. If you search few elements, this is not going to win you anything. But if you search many elements, maybe. But before, there's a number of unexplained things. You know, this whole indexing thing is not everything is indexable. You know, there are some ranges like, you know, like iterators, you know, input forward, bidirectional, and random access is the most powerful. So not everything is indexable. The worst thing is that this guy may throw. And that's pretty bad because if this throws as the scope is exited, I have two problems. I have an exception and I have a range that I changed inadvertently during the search. So I want to make sure that that operation never throws. And indeed, for some types, it's not going to throw. Incidentally, they're exactly the types for which this optimization would make sense because they're cheaper to compare, right? So, But wait, it gets even worse. Find itself doesn't work for all types. You need to make sure that I only pass ranges to it and comparable elements and stuff. So we have like a number of issues here that are kind of in the air right now, and we need to solve. So we need to, for example, not only want to restrict find to work with ranges and their elements, but we want to choose the right implementation automatically with Sentinel for certain types, index for others, and conservative for the others. Right? So we have a number of issues with regard to getting that code production ready. And here's how you fix it. You're going to put a constraint on this find function here by saying, well, range find, range, it only works if the range is an input range. This is it's a library function. It's a library compile time function, I should say. And the type of the comparison of r.front with z is bool. Who likes spin A? Who likes spin A? Who hates spin A? All right, security. So this is like spin on steroids, because if this doesn't compile, if this comparison doesn't compile, it just returns false. It doesn't stop compilation. It says, you know, this is not true. The fact, you know, you're testing that the type of r front equals c is bool, and if that fails, it's just a false. Which means if you try to call find with the wrong things, you're simply going to, it's not going to be there. It's going to bow out, right? Great. So with this, we fixed things because this is all we need to make find the conservative version work. That's going to work with the front pop front thing. Very nice. Word of caution here, because this is important. E must look like an expression syntactically, right? It must be parsable as an expression. You can't put like an unpaired brace in there, right? You can't put like just about anything. There must be something that looks like an expression. It may not be an expression after semantic checks, but it must look syntactically, like grammatically, like an expression, right? So now, okay, so we solved that problem, but how do we choose with and without Sentinel? Enter static if. With static if, we get to choose inside the function. So we have, if is inputted here. Here, actually, I replaced a bit just because there's no space on the slide. I put colon here, meaning the type of this guy converts to bool is not exactly bool, which is fine. If it returns int, I'm fine. All right. Static if the range is random access and has slicing, because I'm using slicing. Here's the slicing. This is a slice, right? I'm taking a slice from the range. So if the range is random access and has slicing, then I need to use either sentinel or index. Sentinel if the range is writable, and index if it's not writable. Because there may be a range with immutable elements, for example. You can't write to them, right? So then how do I test that that operation doesn't throw? Well, I'm going to write a lambda, and I'm going to try to take its type. The lambda is no throw. What if this would throw an exception? This doesn't compile. This is a capability check. In C++, no except is not checked statically, right? Debatable decision, to be euphemistic about it. Debatable. Right? What? Is that checked or not? It's not checked, right?
Becoming part of the type system, no exception.
It's becoming part of the type system?
Yeah.
Meaning it's going to be checked?
You can check.
You can check it if you so want. Yes, great. Terrific. So here I'm going to say, is the type of, I don't care if the type is something, I know the type is going to be the type of a lambda returning void and being no throw. But my point here is that I insert some code that must not throw, and I put no throw on it, and I check the capability, and I'm done. So if this so happens that I can assign to an index access into the range something else, it doesn't matter. Then I can use the Sentinel implementation, and otherwise I can use the index implementation. And if nothing works, I'm going to have to use the conservative implementation, and that's how I select 3 algorithms, completely different depending on the capabilities of the types that I got. Make sense? It has a name. I gave it to it. It's called design by introspection. And if you hear of it later, I liked it before it was cool, right? All right. Please note, this is a very old technique. However, when people implement like find originally in the STL, they can't use it. They can't use it. Why? Like, in classic C++, C++03 through 11. Why can't you use the Sentinel technique? Because there's not enough introspection ability of the language that allows you to check for these things automatically and choose the right implementation. So you can't use it. So even though this technique is old, it was not applicable. So my point here is that good introspection is important because it allows you better algorithms, faster code, which is a weird conclusion. It's a good point, but it's not obvious. Right? Faster code means you need a language with better introspection. I take by your silence, the thundering silence, that you agree. Are we together in this? All right, raise your hand if you think the same, my friends. Huh. All right, I'm getting some hands. That's great. All right. These are not only applicable for optimization, they are applicable in a million of other situations, especially static if. In static if, you're going to find in this standard library that it appears every 88 lines as word count counts, as WC counts. And the standard library has the documentation in it. So it's every 88 lines with the documentation. So if you take the documentation out, it may be like every 40 lines. That's huge. Every 88 lines. It's huge. Used everywhere. And here I talked only about behavior, but you can mold structure because you can put static if condition and you put a field in a structure depending on something. And it's amazing because you can actually change, you can tune you can put the atoms with your hands and create gold or any compound you want, any composite you want. It's amazing. All right, so, but let me make a point here. This is not about D. It's not about D. It's about you, because it gives you insight into how you can optimize things. So let's get back to the optimization topic. I'm not going to insist more on these language things. Well, let's see if the optimization helps. So we have the time and we have the input size, and this is the time taken by a failed search, which is going to exercise my, right? A failed search is going to go all the way through. So that's what I want to measure so I can estimate how much gain I get in the best case, right? This is a failed search. Time in milliseconds, input size in millions of elements. And we see a nice speed up because this is the baseline. The red is the baseline, and the blue is the sentinel technique. Very nice. And just to make it clear, I divided the things. I'm measuring the speed up here. So look at a pretty neat speed up. 10 to 50%. This is awesome. Because fine, I mean, anybody's liable to do a linear find once in, right? It's not nice, but you got to do it sometimes, right? It shouldn't be called find. It should be called find. You got to do it sometimes, right? It's a long. Got to do it. It's good to have an optimal find, right? You think I'm cherry picking this? I mean, this is old news. Like everybody knows about sentinels. Or worse, they don't know because they've been forgotten, because they've been invented in what, like in 1956, right? So you think I'm cherry picking? I'm not. Sentinels are much more widely applicable to much more complicated algorithms. Let's take a look at something else. How about Tony Hoare's partition? Partition is the workhorse under sort and the selection problem. What is the selection problem? In STL, how do you call it? Someone else. Have you been in my class? Some nth element. Thank you. Very widely applicable, right? So we have partition. You choose a pivot, and you're going to put everything that's smaller than the pivot to the left, and everything that's greater than the pivot to the right. Awesome. So how do we apply sentinels to that? It's not obvious. Let me show you the baseline. So pivot partition, I'm not going to insist on all of those introspection things. I'm just going to assume they are done. So we'll focus on the code. I'm going to swap the pivot into the first position. This is the first thing that that Hoare's partition does. And then I'm going to walk the range from both ends. And whenever I find two elements that are one is in the wrong place, the other is in the wrong place, I'm going to swap them and continue. And when the two indices meet, it means I'm done. And I return the position of the pivot. This is how Hoare partition works. By the way, this is already a highly optimized baseline. Let me give you a tip here. I mean, some infinite loops here. That means you kind of even like, what's this? It's a label. And what's this? A label break, right? I want to avoid, because otherwise I need to do one more test here like an idiot. I don't want to do that. I want to do the minimum testing possible, right? So here, so my tip was the following. The fastest code is going to use a lot of infinite loops, which is paradoxical, right? They're infinite, they never end. So, but I'm not kidding. If you want to write fast code, start with an infinite loop, because it's the most core construct that's possible. It's just whatever you have with a jump at the end, right? That's it. And inside, you get to choose your conditions and things. Most people are mentally blocked by the notion that they must insert the test here at the top of the loop. And very often, it just so happens that it's better to marshal code differently in a way that the test is not done at the top of the loop. So you're going to get faster code if you start with an infinite loop. All right, if you take one thing from ACCU, this should be it. I'm not kidding. No, if you take one thing from this talk, let's say, okay? There's other much better talks, right? So, all right, so this guy is going to find from the left. He's going to push low from behind, from the number 1. And if I reach the limit, I'm going to break from the entire loop, and essentially I'm done, right? But if I found a misplaced element, then I'm going to break this little loop here. And I have another little loop, which is going to say, well, let me go from the left to the right. And again, if I reach if the two indices meet, then I'm going to break the whole loop. And otherwise, I'm going to break here. Here, I'm going to swap the elements. I'm not going to make progress. Right? I don't expect this to be understood in every detail. But let me tell you one thing, which is very interesting. This has been implemented, of course, many times in many libraries. And one mistake that's worth talking about a bit is here. Here I'm using greater than or equal. I'm not using greater than. Here I'm using greater than or equal. I'm not using greater than. I should, because at the best I want to push these limits as much as I can before I need to swap. So why am I stopping at greater than or equal? Why do you think I'm doing that? I'm trying to conserve the order. No, this is not stable. But you. Sorry?
So if the two elements is equal between each other, you are trying to conserve the position one related to another.
I understand what you're saying, but that's not the answer.
It would be an infinite loop if all elements are the same as the pivot.
No, because I have here. I'm breaking from the whole loop.
Okay.
So I'm testing. There's no infinite. So it's gonna work. It's gonna pass. It's gonna pass unit test. But there is a bigger problem, which is very subtle. What if we have, yes? If all elements are equal, what's gonna happen? If everything is equal, that's a good start. This is where we want to be. If all elements are equal, or most, right? So I'm going to just go through with the left guy. I'm going to go all the way up to the right-hand side. So I'm going to return that the pivot is at the extreme right. Thank you. What's the problem with that? It's subtle. The problem is fairness. I want to partition, and I want my pivot to be as much in the middle as possible. Why? Yeah, I kind of want to have things, because partition is most of the time used in quicksort. If you put greater than here, I swear to you, quicksort is going to be quadratic for ranges with a lot of equal elements. It's amazing. One character, you change one character, it goes from n log n to quadratic. And people did that, made that mistake. It's very subtle. It's very easy to make. I made that mistake. There's an early implementation of a sorting routine. And I was an idiot, because I just didn't read the literature properly. Very interesting. So you want to have some fairness in the system. So whenever it's like greater than or equal, you stop, you swap. Even if you swap equal elements, that's still better than quadratic, right? So what you want is kind of keep the equal things kind of where they are, right? Excellent. So we found both bounds. So we come from the left and right. We found two that are misplaced. We swap them. We go on again and again and again. When they meet, we're done. This is a highly optimized baseline. All right. I'm giving you the ball here from, I'm going to throw the ball, make it faster. Ideas. Ideas to make it faster. Yes?
So the pivot is a sentinel in one direction.
Put the pivot as a sentinel.
The pivot is a sentinel and searching in one direction.
The pivot is a sentinel when you search, in this case, because we had the pivot at the first position there. When I search from behind, I can eliminate this comparison, presumably, right? Yeah, that's right.
Roughly speaking.
Roughly speaking. You're on the good track. Yes. Other ideas. And actually, this is done. Yes. Other ideas from other people.
Oh, from other people.
Okay. Other ideas from Dietmar. Yes. Destroy.
Okay. Once you have swapped elements, you know that there's a pivot at the other end as well.
Once you did the first swap, you know that there's a good pivot at the other end. Now we're getting somewhere, right? Yes.
There are lots of equal ones. Rather than having the grid values there and always swapping lots of them, could you change it that you unroll it a couple of times and only do the equal check occasionally?
If you have a lot of equal elements, can you test before swapping?
Well, you move the greater to the equals that you're putting there to deal with the non-equal points you just talked about. Makes it a lot slower because you do a lot of pointless swapping.
Right. If there are many elements equal, I'm going to do a lot of pointless swapping.
You don't need to do that every time. So if you unroll it a few times, your volume, and only put the greater than or equals in one of the copy space.
I think you got something. I'm not understanding exactly, but I think there's something there. So let me make sure I understand. This is going to apply for ranges with many equal elements?
Yes.
Okay, good. Let's look at something that's going to apply always. It's going to be strong. So, we're looking at some interesting sentinel ideas. So let's put a sentinel. We have it on the left. Let's put it on the right, and let's do interesting things, right? So let's see how I can make it faster. So, as I said, currently, find from left, find from right, swap, make progress. This is my algorithm. Yes? We're done when the indexes meet, and we have many index checks interspersed with the actual computation. So I want to, we're on the routine to focus on work and not overhead. This is kind of a basic thing to want. And we can't plant a sentinel in the middle because we don't know the final position of the pivot. All right, here's the idea. As Dietmar said, plant sentinels at both ends. So first thing I'm going to do, I'm going to make sure I put the pivot at both ends. I'm going to save in temporaries and whatnot. So I'm going to just save the state there, right? And here's the interesting thing that I think you're going to like this. You know what the vacancy is? Like, not the kind you don't take enough of. Not holidays, right? A vacancy like in an atom. What is that? Yeah, so an imperfection in a crystal and there's a missing electron somewhere, and whenever there's an electron missing, another could take its place. But what happens then? You have another vacancy where that guy left from. So these vacancies tend to have like their own behavior. They have a life. They move. And actually, yeah, this is how the semiconductors work. They move vacancies around. So let's do the same. Right? Why the hell not? Let's do the same. Let's create a vacancy in the range. So we plant the sentinels, and then we'll create a vacancy in the range. We essentially remove an element from the range. We make it disappear, and it's a hole, a vacancy. It's an imperfection in the range. And next, what we're gonna do is we're gonna fill the vacancy. So we come from here, we fill the vacancy, and then we leave a vacancy here. Then we come from here. We fill the vacancy here, leaving a vacancy there. Right? And that's how the bubble goes. And the bubble is going to move up to where? When's the bubble going to stop, the vacancy? At the final position of the pivot. Amazing. It's exactly what we wanted. I can't believe it. And then what am I going to do? I'm going to pop the guy I took. I'm going to put it back. Poop. Oh, sorry, I said poop. Jesus. Am I allowed? Thank you, John. All right. I'm going to put the thing that I took, and I'm done. And instead of swapping, each swap is really like, it's 3 operations, temporary, right? I'm doing half swaps. I'm doing half swaps by filling these vacancies. All I do is, I'm doing half a swap, and then the other half I'm going to do from another place, right? So I'm going to save on swaps. I'm going to save on index computation because of Sentinels, and I'm going to have a faster partition, which is amazing because nobody improved it in, what, 61? What? We're looking at what? 55 years. We're going to today improve a routine that has not been improved in 55 years. I'm not kidding, I'm not exaggerating. Are you ready? All right, here's some shit code for you. All right, so it's a long function, so it's not trivial. I don't expect you to put a finger on anywhere, but I'm going to describe it in you know, from a distance. John, how are you on time? What's the time? 15 minutes. Terrific. All right. So, pivot partition, if the length is too small, I don't care. I'm going to put a pivot at the front, and I'm also, as I said, I'm going to create a temporary, and I'm going to plant the pivot in the end as well as a sentinel. So I'm going to say save is the last element, and I'm going to plop P into the last element. And from now on, I consider I have a hole at the last position of the range. So what's the next thing I'm going to do? What search am I going to do now? So I have a hole, I have a vacancy at the very end of the range. So now I'm going to start from the left of the range, right? Trying to find something to fill that vacancy. Awesome, here we are. So I'm going to go up, and then I'm going to fill the hole. And then I'm going to go, now I'm going to have a vacancy here. So I'm going to come back from this side, right? And then I'm going to fill. And by the interplay of the sentinels that I have here, I only need to do one test that's not work. Everything else is work in this loop. Only this is not work. Only this is sort of, oh, this is management overhead, right? Bookkeeping, friends, bookkeeping, not management, bookkeeping, all right? So this is my overhead. One line in a large-ish loop, right? Other than that, I'm just doing work because I do need to compare against the pivot. This is a given. I do need to compare against the pivot. This is a given, right? These increments are part of life. They're also sort of overhead, can be considered because they're indices, right? But I need to do them. But the only comparison I'm doing is here. 55 years, right? Am I the smartest guy in the world? No. No, I have a lot of reasons to be modest. Good reasons. Because actually, so I invented this. I thought I'm awesome. And then I did some literature search. It turns out that some Indian guy, two guys invented it in 2011. Right? So 50 years. 50 years. It's a research paper. I have a slide on it. But, you know, I felt for a few minutes there, I felt really good. Right? And it was worth it, right? All right, so this is my innermost loop here. It's going to go fast, really nice. And in the end, something weird is going to happen at the end. Because in the end, the pieces are going to be on the floor, and I need to kind of fix up things, kind of restore things. And And it's just that I figured that the worst that can happen is that low and high, they overshoot each other by 2. They could overshoot each other by 2, 1, or 0. It's just the way the loop works. So you got to treat each case with attention. So this is not, again, this is not easy to understand, but in essence, you need to handle all of these possibilities. So if I overshot low and these 2 by 2 elements, then I'm going to do a little fix up here, and I have another here, and then finally I'm done here. I'm going to swap back the pivot, and I'm done. Terrific. Is this going to be faster? All right, let's see how much faster. And by the way, so these measurements, they were part of the build of these slides. I didn't kind of paste a graphic. No, I use LaTeX. So I say make. I use a make file. And part of make is it runs the benchmark, and it produces a data file, which is read into LaTeX and is formatted beautifully here. So these are as fresh as they get. I built them like this morning. I'm not kidding. Every time they come a bit different, which is funny. Like, there's minute differences every time, right? So we're looking at not a huge improvement, but a good improvement. And what's nice is, again, this is a function that's very important for quicksort. It's everything quicksort does, because what does quicksort do? Partition, partition, and partition, quicksort, quicksort. And what does quicksort do? Well, partition, quicksort, quicksort, and so on. I could spend the rest of my talk saying this, right? So, awesome. The relative improvements, we're looking at 0 to 30% improvements. Very measurable. Very nice.
You get that from the same executable?
I got them from the same executable, yes. Why is that?
Yeah, you could run make twice.
Oh, I could run make twice, yes. Good point. Actually, no, there's trials inside the benchmark that repeat. But there's a number of things we can do to measure better. But this is good. This is great because again, we're looking at something that has not been improved in 55 years, and it's awesome to be able to do so. So as I said, I thought I invented this. I was feeling very happy. But if you search for the paper Engineering of a Quicksort Partitioning Algorithm by Abhyankar and Ingle, you're going to find that it's been done in 2011. It has not been done in 71, right, which is interesting. It's been done recently, right? So now you know what to do. Standards, folks, you go to your STL implementer and you say, do this. Right? Right? All right. Don't mention it. Really, don't mention me, okay? Awesome. So, that paper, however, is not as sophisticated as my algorithm. Because it doesn't allow you to choose any pivot. It chooses a pivot for you, which is the first or the last element, and then it uses that as a pivot, which is a problem, right? They have a simpler function because they don't need to do all of this overshooting thing. They don't need to worry about this fix up here. So it's a lot simpler, but it's also a lot less flexible, right? But anyhow, they had the same vacancy idea, which I think is very remarkable, and you can use it in many places. It's pretty awesome. Love it. And you may think I'm cherry picking this, but I'm not. You think I'm cherry picking? Oh, so he chose like 1, 2, 3 algorithms that he liked. And no, I wasn't looking for sentinels. I was looking for a faster partition. And this came about. What can I do? It's not my fault. Don't shoot the messenger. Right? But there's a lot. And once I discovered that there's a larger pattern to Sentinel than just linear finds, I was like, Jesus, they're everywhere. They're like aliens. Everywhere. Dot product. What's dot product? Dot product of sparse vectors. They're sorted. you know, they're sorted by index, two sparse vectors, sorted by index. Each element is an index and the value. And it's sorted by index, right? And you walk them, and you want to compute a dot product, which is like you multiply the elements that have the same index. How do you apply a sentinel there? Ideas. Dot product, sparse vectors, each element is an index and a value. You need to multiply all elements with the same index and sum them together. Add a final entry with the same index, so no matter how you go, you're going to get there, right? Or even simpler, you don't need to really add. You only need to overwrite the index of the last one with the smaller index with the greater index. And then you just go through it. You only check when the indices are equal. When one of the indices is smaller, you don't check, you save. Awesome. But wait, there's more. Set intersection. How do you apply that to set intersection? There's a function in the STL, set underscore intersection. How do you apply that to it? Huh?
Add something to the two sets.
You don't need to add. You overwrite. You overwrite. The last one, again, with the largest of the two. You overwrite, and then you just blaze through it. Set intersection. You need introspection. You need to fix that no except, God damn it. You need to fix that no except. It's like ridiculous. What's wrong with you? Marshall, what's wrong with you? Who did that?
Alphabetically or?
Alphabetically or by seniority. You gotta fix introspection. You gotta have, without introspection, code is slow. Do you like slow code? Who likes slow code? Raise your hand. All right, set intersection. Merge. Merge, same thing. These three, they're the same pattern. By the way, so this is like the greatest interview question ever. So I asked candidates for dot product. It's just, by the end of the interview, the candidate is 10 years older. I'm not kidding. Because it's so much theory and practice in there. It's just amazing. All right. Merge, same thing. Lexing and parsing. How do you apply sentinels to lexing and parsing? Ideas. Lexing, I have a big hunk of text I need to lex and parse. How do you, I have a big hunk of text I need to parse. C++ source code, if you wish. How do I, come on, Jesus, guys, you put a 0 at the end, you put a sentinel at the end, and you have a big switch, and your big switch is going to treat 0 out. It means I'm at the end of the range. The upshot is you don't need to test for each character whether you're done or not. Huge gain. Huge gain. Amazing. Make sense? So you put a sentinel at the end, and then you just blaze through, you parse, and it's a token. It's the end token. You don't need to check whether you're done or not. Otherwise, you need one check per character. By the way, may I say one more thing I like about C++ concepts? Do I have time?
Yes.
All right. To my demise. Okay, here's the thing. Do you know Hello World, how big it is? It is. Like Hello World, you build Hello World, and how many lines do you get after pre-processing? Too many. I just measured this morning with Clang. It's 37,000 lines. You know, people say C++ compilers are slow. They're amazing. They're amazingly fast. It rummages through 37,000 lines of code in like a second. It's amazing technology going on there. It's fantastic. It's like, and you know, that's Hello World, but it only gets worse from there. It doesn't scale. It just goes worse and worse. We've had code, it's like, I'm not kidding, 25 megabytes after pre-processing. One file. I mean, the sheer fact that you can parse that thing, it's just amazing. Compiler technology in C++ is blazingly fast. It just has a lot to do. Right? There's a lot of work there. So now we have the situation there, right? And then, guess what? People come with C++ concepts, and we want concepts to be checked for all templates without you using the templates. You never use them, but we want them checked. On the assumption that somebody may have delivered a library to us that they never unit tested. They delivered code, they never instantiated to even check. On that assumption, they want all templates to be checked early. Those 37,000 lines of code contain obviously a lot of templates because they're in the headers. A lot of templates. And now we want to not only spend time on parsing that text, we want to spend time on checking that as well. Right? Ridiculous. Do you agree? Agreed? Yes, okay. I'm trying to collect names here, and I should. I'm signatures, okay? Sign the release form after this, okay? Ridiculous. I want to check things on the assumption that some idiot delivered me a template that they never care to even instantiate in their life to make sure it at least kind of does something, at least it compiles, right? So anyhow, let's get back to efficiency. All right, so my point here. There's treasure everywhere. You can find good things to optimize everywhere. You just have to find it. How do you find it? By using introspection, right? So, I'm going to write a book. I have a great title. I need to write the rest of the book. Scott Myers granted me the title. It's his title. And he was very nice because it's a great title. So again, I have the title, I need to write the rest. Fill the blanks. Right? Fastware. A lot of optimization techniques. Here are some things, and I'm going to talk just half a minute about each. Benchmarking techniques. You know that most people don't know how to benchmark, so this is going to discuss that. Strength reduction. You replace the stronger operations with simpler operations, changing algorithms for fun and profit. Right? Cache friendliness. How to arrange things such that you have better cache friendliness. Use less indirect access, avoid indirect writes, things like that. Indirect write elision, how to get rid of writes through pointers, which are the worst kind. Right? Memoization and obliviation. Obliviation is a word that I invented 24 hours ago. It's the opposite of memoization. John Laker said, what was the word? Ignorance is better. And I said, you're ignorant. That can't be, etc. Ignorance. So memoization is I'm saving computer data. Sometimes it's better to recompute it in some subtle cases, and let's call that ignorance or obliviation. Who's for obliviation? Who's for ignorance? The people spoketh. All right. Hoisting and lowering. What's hoisting and lowering? Hoisting. It's a classic compiler optimization, actually. It takes things out of loops. You take things up and you compute them once and you're done and awesome. What is lowering? The opposite of hoisting. I put things inside. When do you want to do that? When you unroll, for example, right? When you unroll, you want to lower. Lowering also has a different meaning, which is you want to replace higher-level constructs with lower-level constructs, and that's also sometimes affecting optimization. And a lot more. There's so much stuff. There's just so much stuff that's good there about writing fast software that I learned in 5.5 years at Facebook, and even before that, I'm bursting with enthusiasm about this. All right, with that, I'm done. Thank you so much. Thank you. You've been great. Thank you. Do I have a minute for questions, John? Yeah. Questions? Questions? Yes? No, loud. Yeah, ball. Give him the ball.
It's like a mic, okay.
Oh, that's heavy. Okay.
If these things you're talking about in the last slide are compiler optimization techniques, why should we be spending our time coding to those when the compiler will do it for you?
I understand. So these are compiler optimizations. Why am I talking about them in a book on optimization? These are also optimizations that you can do by hand in the very often cases when the compiler doesn't. For example, strength reduction. You replace multiplications with additions, for example, right? It turns out that you can change entire algorithms to unrecognizable forms if you look for a strength reduction. And that's not something that the compiler can do. You change the algorithm with one that's... Yes, question? Question? What? I didn't get it, sorry.
Whether you could write the book a little bit faster.
The book, can it be written faster? Okay, good one. All right. Question?
One more question.
One more question. Question for the ball.
Go on then.
All right.
Why did Scott Myers give up on Fastware? I was aware he was working on it and was looking forward to it, so I'm glad you've taken it over, but why did he give it up?
Why did Scott give up writing Fastware? I think he retired. He's just, yeah. All right, we're done. Thank you very much.
So just want to do a quick poll. Who's here is a member of the ACCU? And that's what? Oh, that's 50%, 60%? What's that look like? So for those who are not, want to find out more about the ACCU, we have our stand on the opposite side of that wall. Come see us, and we'll explain what it's all about. Just want to say thank you very much, and thank you very much.
Thank you, guys. Thank you. It's been awesome.